She's going to drink stuff, but making sure she's on this.
You're making a record,
And she's going to do this.
Oh, yes, question.
Where would I go for the blood guys? Like,
I don't know.
It's a shamrock.
Shamrock Golf.
so they'll just come back.
Is it Shamrock? Hall?
Yeah,
Yeah, Shamrock Golf.
Okay, so let's finish off with this chapter, and you will be. Is there a homework assignment due soon? The 20th. And after that, you have a test to be taken before you come back after Thanksgiving break. Alright, so let's complete with this chapter. So what do you know so far on electromagnetic induction? Do you remember all the equations that we have come up so far? EMF on a conductor cutting flux lines. EMF is equal to BLV. So you know that part of it? We went through that formula last class, and you know how to apply it. And also you should know how to know the sense of the EMF's polarity, like, you know, which is positive, which is negative. That's something important. So it could be just as simple as this side or that side is positive. But unless you really apply Fleming's right-hand rule and find out which way the induced current would probably flow, then only you can find out which side is positive and which side is negative. So we were talking about generators in the last class, all right? AC generators. So the AC generators used slip rings, right? So the AC generators, they use slip rings. That's one ring, that's the next ring, and that's the axis of the generator. So as it is spinning like this, the two brushes, brush number 1 and brush number 2, they tap out the voltage that's coming out from these two slip rings. These are slip rings. And the voltages that come out from here are alternating, and you saw that. It was alternating. Sometimes this side is positive, and sometimes the other side is positive, and so on. So the induced EMF is alternating, so also the induced current will be alternating. And how many times it alternates per second is the frequency F. So the frequency of this voltage that is generated is F, and we saw that the peak was what? Omega BAN, where omega is 2 pi F. That is a peak value, and the whole equation is the EMF is equal to omega BAN sine omega t. That's the equation for the generated EMF. And this part is the maximum, so EMF is equal to Emax sine omega t. Now that is an AC generator. Now if you use a DC generator, now what is a DC generator and how is it going to be structurally different? In a DC generator, instead of slip rings, they use split rings, which is the commutator that you saw already, right? Do you see the commutator for the motor? The motor had commutators. So instead of slip rings, they use split rings. That's a split ring, and the brushes are actually connected to the opposite sides, just like a motor. And so what will be the consequence of this? The output that's going to come out, will be, so whichever wire comes on this side whichever wire comes on this side is going to push the voltage from here. So this will be positive and that will be negative at all times. Because when this flips, the commutators just exchange places. But still the conductor which is here is moving in one particular direction, therefore induces the same polarity on this side. And so when you plot this over here, what's going to be the shape of the graph? The shape of the graph is going to be this. So you won't have the negative peak, negative part. So in other words, this part is flipped. You see it? Do you understand this part here?
No,
DC. This is DC. See what's happening over here? What's happening over here is this brush collects any voltage that is picked up by this conductor. You see it? Now when this conductor on this is on this side, it is generating voltage in one direction. But when it flips to the other side, it is generating voltage in the opposite direction. So this brush will collect positive, negative, then negative, positive, then positive, negative. It flips. Whereas over here, it's always positive and negative. Yeah.
Piece like, do the slip rings, do they rotate with the
They rotate with the coils.
cool.
Yeah.
So I'm kind of confused how it changes. Oh, never mind.
Try to think of this.
Yeah, I did.
Look at this coil, then you'll see it. So right now, let's say the magnetic field is down, 3. Okay. So let's say this is turning counterclockwise. So that means this conductor is actually moving down. Magnetic field is this way. And the conductor is moving down. So that's a force. Right? It's turning like this. So when this conductor is moving down and the magnetic field is towards in that direction, which way is the induced current? Which way? That way, right? Right hand rule. Magnetic field, force. Induced current is towards us. So the induced current is going to come this way. And it comes out from here. And it comes to this slip ring. And it picks up, and therefore that's why we say this side is positive. Now what will happen when this conductor moves to that location and that conductor comes and places here? So imagine this picture is now this conductor, let me call it A, B. Let's say B comes in place of A and A goes to that side. Now what's going to happen? The magnetic field
Tries to right the loop to being in its lowest energy position.
I didn't follow what you said.
The magnetic field tries to put the loop in its lowest energy position, and we tap the current that's created during that.
Lowest energy position. What do you
Like
mean?
where it's not moving, it's trying to make it not move, but then because of
The induced current which is actually produced is flowing in a direction to oppose what is happening, and that is what causes the induced current. So when you're, if you think of the electrons, many electrons on this material, you'll understand how it is happening, because all these electrons are going down. So think of force on a moving charge, and that will help you to understand which way the induced current is coming down. So it's basically electrons going down. There's a force on those electrons, and the force on those electrons is what generates the push of electrons, and that is your induced current. Now, for convenience, we are using the Fleming's right-hand rule. It's only a convenience thing. So immediately find out which way the current is flowing. That's why I said if the thing is moving down and if the magnetic field is that way, the induced current is going to be this way. if you want to look at it as electrons, so this is an electron, that's an electron, that's an electron, that's an electron. When this part of the conductor moves down, think of those electrons moving down. So use Fleming's left-hand rule for it. Which way are the electrons going? Downward. So which way is the equivalent current for that? Upward. So current is upward. And magnetic field is that way, using Fleming's left-hand rule. So which way are the electrons going to be drifting? Inward. So the electrons are going to go this way. That will create a current which way? That way. You get it? So the induced current is as a result of all these processes, but to make things easier, we just use the Fleming's right hand. Yeah.
So what's the difference between using the left hand and the right hand? Like what situation?
Left hand for motor effect. Right hand for generator effect. GM. G for generator, M for motor. Okay. Remember it any way you want. This is motor effect. What's motor effect? You have a current flowing through already in a magnetic field, and that conductor experiences a force. That's called the motor effect. The force comes as a consequence of the current. This is different. The generator effect is if there is a conductor which is made to move in a magnetic field, an induced current is produced. So that's why it's called a generator effect. So motor, generator, induced, and here is motor effect. All right, so you understand this. So what happens if you have more commutators? It actually gets like this, but still it is fluctuating. It is not steady. You can see that this is not steady. And to make it steady, what we do is this. To make it steady, what we do is we connect a capacitor across this. A big capacitor. So what happens now? If you connect a capacitor across the output, what happens now?
Charge something.
What happens? The capacitor will charge up. So that means as soon as the first part of the cycle comes in, as soon as that part comes in, the capacitor is getting charged. So the capacitor charges plus minus. Then what happens at this point? When this one goes down like this, will the potential difference across the capacitor die immediately? It will hold on. It's not going to get discharged immediately. So even though the current that was charging went down, the capacitor is going to go down like that. It's going to discharge kind of slowly. Meanwhile, the second pulse comes up and charges the capacitor once again. You understand what is happening? In this part of the cycle, that is 4 milliseconds, the capacitor gets charged. Then when the current went down and when the current is coming back up again, in that period of time, the capacitor will hold its potential difference. And then the second pulse comes in and fills it up a little more. Yeah.
Why is the second not as dramatic as the first, like the charging?
No, because it's already having this much charge, so a little more only is required. It's like filling a water tank. What's the purpose of water tanks? You know, the purpose of water tanks? You have seen those big water tanks. What's the purpose of those water tanks? It's just like a capacitor. Because the water company is pumping water. Now imagine there was no water tank at all. Okay? Imagine there's no water tank. The water company pumps water in the morning. So what will happen? The water will come from this time to this time. From morning 7 o'clock to 8 o'clock, water is being pumped. So what will happen is you have to use your water that time, from 7 to 8. If you don't use the water at that time, now the pumping station, they turn it off, and then you don't have water for the rest of the day. Until evening comes, they pump it again from 7 to 8, and then you can get water. That's so inconvenient because you are getting water only from 7 to 8, one in the morning, one in the evening, which means you have to do your work during that time, and after that the taps are empty. Okay, it is like not having the capacitor. It's not like, see, water is getting filled up, and then now it's turning off, coming back on again, turning off. Now, what do these water tanks do? What the water tank does is, when 7 to 8 it's being pumped, it goes straight to the water tank first and fills it up. Now the water tank is filled up. So by 8 o'clock, the water tank is full. Now what happens from 8 o'clock to evening 7 o'clock? People are using it, right? So the water tank's level is going to go down. But it's not going to get empty. It won't get empty, but it will come down. By the time it comes down a little bit, depending upon the usage, the next pumping time starts off, so it pumps up till it's full. And once it's full, the pumping station turns off the filling. So it's full now. What happens then? 8 o'clock, turns off, this goes down. By the time the next pulse comes in, fills up. So this keeps going on and on. So the output is always kind of steady. It's not fully steady, but it is steady. You see it? The output is not like this. It's not fluctuating with water, no water, water, no water. Here is much better. Water's there. Water is coming down in the levels, but you still get water. All the time you open the thing, the water is actually coming out from here because of the pressure head. Well, is the pressure coming down? As the water level in the tank comes down, the pressure is coming down, but it's not going to make a huge difference to the flow. So the voltage is there, and the voltage comes down gradually, but it's not going to make any big difference to the overall usage. So is it approximately steady? Now if you put a much better capacitor, then what will happen is the storage becomes better. If you have a big tank, what will be the difference? The difference is it won't drop much, correct? If you have a big tank compared to a smaller tank, the big tank, it will drop only a little bit by the time the filling time is come, and then it will. So if you use a bigger capacitor, then the output will pretty much be like this. It will fill up, and then pretty much there, next fill up, pretty much there, next fill up. So you get almost a straight line. And that is what is DC. You understand? If it's a pure DC, that's what's supposed to be there. A pure DC should have this. The voltage should be pretty steady. And how is the voltage, the steady voltage achieved? By using capacitor. Now that is an adapter. I'll talk about this later also. Now what goes in here is 110 volts AC, right? But what comes out from here behind, what comes out from here is DC, positive, negative. Now how is that DC going to be similar to that is if you use a capacitor to smooth it out. Blood? Okay, go. There we go. Do you see that capacitor sitting here? The purpose of that capacitor is to smooth the output. And we're going to talk about transformers right now. So that is the capacitor which actually makes it smooth. Now, a bigger capacitor will make it better. So good adapters will have better, larger capacitors, and the capacitors are required to make the output smooth. Now you can see 4 other little components here. Those are called diodes. And I'll show you what the diodes do. Alright, so you understand how the output is coming out and how is it AC and DC and all that. Okay? Now, so remember, this induced EMF is a back EMF. You know why it's called back EMF? Why is it called back EMF? Because it's an EMF, or it's an induced current that flows in such a direction to oppose the cause. So if you are trying to spin the generator, it will try to prevent you from spinning the generator. And therefore, you have to put in more work to spin it. And if you put in more work to spin it, it is generating the electricity. Do you get it? That means the work that you put in is what generates electricity. That's why it's called back EMF. It is not an EMF that helps you to turn it. It's not a current that helps you to turn it. It's a current that prevents you from turning it. Do you get it? So to spin a generator, you have to put your effort. It's not easy to turn the generator. It's not easy to spin a generator. You have to put effort to it. So in a generator, if no load is connected at all, then it should be easy for you to turn. But if you connect a load there, it will become harder for you to turn. How many of you know of a bicycle generator, dynamo? So, okay. Now, if you engage the dynamo on your wheels, but you don't turn the light on, the lights are not turned on, but the dynamo is already connected, it won't feel at all as if you are doing too much work. It'll be just normal. But turn on the lights, and immediately you'll feel the hardship. You will feel it because now you are actually spinning the generator, and the generator is trying to prevent you from spinning it. So that's why the EMF generated is generally the back EMF. Now there is another problem with these generators. Where are these wires wound? Where are the wires wound? The coil. Is it in the air just like that? Where is it actually wound? You saw them.
After school, $1 first. It's a cop. It's actually such a big deal. I've had it for like 6 months. $1. The screen protector. The case is like never seen an app after.
Yeah, this case, I don't see that capture on it, so I didn't have to get some because it has like these numbers.
Yeah,
So I like it.
this has a raised edge too, but it's just makes me safe.
Yeah. But like this is like it's like
The wires. Where are the wires actually wound? The wires are wound on a core. The wires, these wires, are wound on a core. There's a core there, like that. There's an iron core. What's the point in having the iron core? What's the point in having the iron core? Huh? Increases the magnetic field. So the iron core serves this iron core. Serves these purposes. Increase magnetic field which means definitely that's an important factor because you know the EMF induced depends on what? Omega, BA, and B, the strength of the field. So if you put a ferromagnetic material over here, it will definitely increase the strength of the magnetic field, which automatically will increase the EMF. So instead of just having air core, if you wound it on something like solid iron, then you can get increased strength. Not only increased strength in of magnetic field, increase mechanical strength. It increases the mechanical strength. What do you mean mechanical strength? Instead of having a wire that is like hanging in the air, it will be so flimsy, right? It won't have the rigidity. But if you wind it on something firmly, it will stay. Increase inertia. And you know what is inertia? Tendency of an object to keep going, right? So if the core has got inertia, see this one has inertia, it wants to keep going. It wants to keep spinning. So once it begins spinning, it wants to keep spinning because it has inertia. So the iron core actually helps in multiple manners, but there is a problem. The problem is, isn't the iron core also like a coil? Isn't it metallic? Now, if there is an induced current that's actually coming into the coil, won't there be an induced current in the core? There will be an induced current inside the core. As the core is spinning also. The core is spinning. The core is spinning, and so what happens? Just like how an induced current is induced in the coil, which you're tapping out, there is a very strong induced current in the core of the material, inside the core. And that current flows in such a direction to oppose the turning effect. Oppose the turning effect, which means what? The force acting on this induced current is going to be in the opposite direction. So you're trying to spin the generator this way, but it is trying to push you back, which makes it harder for you to turn. And these currents are called eddy currents. Those are called eddy currents, E-D-D-Y. Eddy currents are really bad in this particular generator. Why it is bad? Because the eddy currents are very strong short circuit currents that are flowing in the core, and because it's a kind of short circuited current, the current is going to be high, and that will produce a strong opposition. You saw when that metal ring was, you know, when the magnet was dropped through the thing, see how the magnet went slowly? That means see how much opposition is going through because of that current induced. That current that is induced in the metallic core, that is called eddy current. And eddy current is something bad because it actually destroys the whole act of generation of electricity. Yes, it is generating electricity, but it gives more hardship for you to turn, right? And how is this eddy current minimized? Eddy currents are minimized by what is known as laminations. So this iron core is not one solid core. The iron core is not a solid core like this. What they do is this. They chop it off and make it multiple sheets put together. They cut the cylinder into lots of slices, like bread, you know. You can cut the bread like that into slices. You get it cut already, right? So imagine you have one big loaf. You can cut the thing into slices. Just like that, the core is actually sliced, and this slicing is called lamination. The slicing effect. You chop it like that, and after they chop it, They take each of those and dip it into varnish. They dip it into a special paint, and then they put it together. Now, what is the benefit of that? The benefit of chopping it into sheets and stacking them together after insulating them, you get the increased magnetic field still there. You get the increased mechanical strength. You get the same inertia. You are minimizing this current, because once you chop it into sheets like this and insulate them, you can't have a current running like that. You understand? That eddy current is minimized. How is eddy current minimized? By laminating the core. Eddy current is minimized by laminating the core. You can't get rid of eddy currents completely, but you can minimize it to a great extent. So if you look at these, the core that is actually here, it is laminated. Okay, the core is laminated. Trying to see where the other big one is. This is another example of, this is a transformer, and you can see the lamination from the transformer. Can you see the core is not one solid piece? Can you see it's made up of sheets? They're made up of sheets. I'll pass this around. You can see how they have made it into laminates and stacked them together. Okay. How it is made into sheets and stacked them together, that is and you can see the little paints out of material. Yeah. So what is eddy current? Eddy currents are induced short circuit high currents that flow in the core because the core is experiencing change of flux. How do you minimize it? By laminating the core, by chopping the core into sheets like that, and then insulating each of those and stacking them together. You get all these properties still there, but the only thing is you're cutting down on that induced current. Well, the current that is through the wire is of course not affected, but the core is affected. So eddy currents are minimized by that. Now, are eddy currents bad all the time? No, eddy currents are pretty useful too. It's just like friction. Is friction bad or good? Of course, friction is very good. Otherwise, you can't walk. You can't run, you can't walk, you can't move from your place. If friction is not helping you to walk, you can't just move from your place. So friction is very, very good. At the same time, it's bad also, right? You try to minimize friction to your best by lubricating stuff and by putting ball bearings, and you don't want friction in some places, but you want friction a lot in some other places. Between the tires and the road, you want friction to be a major thing. But at the same time, inside your car, you're trying to lubricate stuff and you do all sorts of things to minimize friction because you don't want friction in the wrong place. Just like that, eddy currents are also good in some places, but most of the time it is bad. So that's why we have to laminate the core. So the core is laminated. So you can see the lamination here. Do you see the lamination here on this one? They are sliced into very thin sheets and then put together. So, yeah, but if you don't laminate it, this thing is not going to spin. The eddy currents will be too strong, it will burn up and heat up and all that stuff. So the eddy current does a lot of damage that way. So what does the eddy current do? Because it's a short circuit current, it actually causes a lot of heating. So when you try to generate electricity, most of your energy goes in heating this core. And what will the heating do? The heating will destroy the wire, because the wire will get heated up too much that it will start shorting to each other. So the eddy currents are really a bad thing for any motor or any transformer. It's a bad thing. That is why lamination is the only solution for getting rid of eddy currents. So eddy currents are short circuit induced currents which flow in a direction to oppose the cause And so the current is so strong that it causes a lot of heating effect and opposition to the generation. Minimize it by laminating the core as you see there. And it is nicely tucked in, tightened up with bolts. So it is definitely going to be solid. Yeah, and the electrical insulation is very thin. It is just thin enough to stop the flow. That's it. You don't want the flow of current inside here. Once you stop the flow of current, then no chance of eddy currents. But can eddy currents still flow through each of those sheets a little bit? Yes. That's why I said you can only minimize it. That's why it needs to be laminated by making it very thin sheets. If you make it thicker sheets, then you're going to have little current again inside. Yeah.
So what's a capacitor look like, or what's it like built? A capacitor?
I showed you.
Is that like a battery cell?
A capacitor, we saw capacitor in detail.
I don't know.
The two plates and the... Where were you? Didn't you see these capacitors? The capacitors, two plates with an insulation in between, that's a capacitor. That's a storage thing, we did it in detail. Plenty of stuff we did on capacitors, energy of charge capacitors. We did so much on capacitors, so at this point you should know what a capacitor is. Oh, you can bring it back to me. So you understand what is eddy current. Now where is eddy current useful? Eddy current is useful in a moving coil meter. Eddy currents are useful in a moving coil meter. Eddy currents are useful in a moving coil. What's a moving coil meter? You saw the moving coil meters? So in a moving coil meter, where is that coil wound? It's on a core. The coil is wound on a core. Now what if you have a laminated core for the moving coil? What will happen is when you pass 1 ampere, the pointer will go like this and the core also will spin, and the spring is now wound, so it will swing back and simple harmonic motion, right? It will keep swinging back and forth for a long time. What do you call that? Something huh? It is simple harmonic, but I told you, like, you know, if something is like oscillating forever, under what? Damped. Under damped, which means like it goes forever, and it will take a long time for the pointer to settle down on that 1 ampere mark. You don't want it. After you connect 1 ampere, you don't want the pointer to keep swinging back and forth. You want the swinging to stop as soon as possible. So what they do, they actually put a solid core in there deliberately. So when you put a solid core, what happens is this: the solid core is spinning along with the pointer. So when the solid core spins one way, it will induce an eddy current which flows in a direction to oppose the cause. So as soon as it swings past, it tries to kind of slow down or bring it back. And then when it swings this way, the current is flowing the opposite direction. So the eddy current will make sure that this suppression is established. So with the solid core, the thing will, like, as soon as you turn 1 ampere on, it will go like, that's it, done. It is right to the same. So you connect the thing and immediately look at the meter. The meter is already stopped there at 1 ampere. How did it stop there? What suppressed the oscillation? Eddy currents. Okay? And you need eddy currents there to suppress the oscillation. That's why moving coil meters and all those meters, they use solid core. And when they use a solid core, we are using eddy currents to stop it. Have you heard of magnetic brakes?
Oh yeah.
What's a magnetic brake? A magnetic brake is the same thing. You have a solid core and there's a magnet. As soon as an electromagnet is turned on when the solid core is spinning, the solid core is spinning and an electromagnet turns on. If you want to apply the brakes, you turn on the electromagnet. So when the core is spinning, what will happen in the core? Eddy current. Which way the eddy current will flow? To oppose the cause. So that applies the brakes. It's a very strong brake. Magnetic brakes are pretty strong. They use magnetic brakes when the physical brakes are not going to be very effective. Like where, big structures, like those big cranes and stuff like that, they're on rails. And those big structures, if they already start moving, it's hard to stop them because normal braking devices don't work that easily. Okay, the friction effects are not good. They use magnetic brakes. So when the wheels spin and you turn on the magnetic field, it brakes it, applies brakes. So eddy currents are useful in magnetic brakes. Eddy currents are useful even in welding. There's a welding called spot welding. So in a spot welding, they do exactly that. They make eddy currents flow in that particular spot, and the heat becomes so much that it melts it and fuses it. So in welding, they use eddy currents. So eddy currents are useful. Now let's look at a transformer, this thing. What is a transformer? What's a transformer? Not the movie. Transformer is a device that transfers electrical power from one circuit to another circuit. That's called a transformer. A transformer is a device that transfers electrical power from one circuit to another circuit. And what is needed for a transformer is a core. You need a core like this. And the core is laminated. You saw that, right? This is the core. The core is laminated. So it is split into sheets like that. The main thing is a core. You can see that clearly. The main thing is a core, which is laminated. And you know why lamination? To stop eddy currents. And then we have a primary wire here. There's a wire that goes like this, and there's a secondary wire here. This is called the primary, and that's called the secondary. You have two wires, a primary and a secondary. It's wound over the same core. So when you connect a DC here, don't draw this. Don't draw this right now. When you connect a DC here, what will happen to the core? It will get magnetized, right? The core will get magnetized when you turn this on. So if I take this wire and connect it to a DC, the core will get magnetized. And this magnetic field will go here. So if I connect a meter here, what will happen to the meter?
It'll go up and then we'll stop, or it'll go up to zero limit.
It will come back to zero, yeah. As soon as you connect this thing, it will go up, and then after that come back to zero, and it won't show any deflection. So what is the output voltage here? Nothing. You won't get any output voltage here. Why? Because the DC will not change the flux. It will create a steady flux. So what we do is, we connect an AC here. We connect an AC. So this is the input voltage, primary voltage. This is the input primary voltage, VP. When you connect this VP here, what will happen is, this core is getting magnetized, and there's a rate of change of flux inside here. And the same rate of change of flux will actually be linking the other one, because the next coil is also there. And this is called the secondary coil. And when you have a change of flux in this, we will get a secondary voltage here. Yes. We will get a voltage there. And this is the back EMF. This is the EMF that is generated from where? From this side. Is there an electrical contact? There's no electrical contact. It's only magnetic. And this thing is what is known as a transformer. I will discuss this in detail in the next class.
What direction does the current go?
Alternating.
So it
It keeps flipping.